Hey everyone, welcome back to Algebra 2. We are in Unit 10, which is about exponential and logarithmic functions. Today we're going to look at logarithmic expressions and how to evaluate them and what they exactly mean. The inverse of an exponential expression is defined as a logarithm. So it's important that for every function that we develop and use, we have an inverse to be able to undo that operation. So the inverse for exponential functions is the logarithm. So we define the logarithm so that the log base b of a is said to be n if and only if b to that power n would give you a. So for instance, the log base 7 of 49 must be 2 because 7 to the second power is 49. Also, the log base 2 of 1 over 8 is negative 3 because 2 to the negative 3 is 1 over 8. The expression log base b of a is read the log base b of a, which you've heard me say now several times, but I want to make sure that you have that on paper that you can reference. How do I read that statement? The b is called the base of the logarithm, that little number there. And the a is called the argument of the logarithm. Evaluate the following logarithm expressions if possible. All right, so let's practice evaluating. Log base 2 of 4. So what you want to think about in your head is 2 to what power would give me 4? Well, 2 to the second power is 4, so that's 2. Then think 2 to what power gives me 8? 2 to the third power is equal to 8. This one's a little more challenging because it's got this fraction. So we're thinking 2 to what power gives me 1 over 16? Well, hopefully you realize that a negative power makes this 1 over. So we know the answer is a negative number. Once we identify that, then we just got to think 2 to what power is 16? Well, that's 2 to the fourth. So 2 to the negative fourth would give me 1 over 16 because the negative would make it 1 over 2 to the fourth, and 2 to the fourth is 16. Log base 3 of 81. 3 to what power is 81? Well, 3 times 3. 3, the first power is 3. The second power is 9. The third power is 27. And the fourth power is 81. So this is 4. Log base 10 of 1,000. 10 to what power is equal to 1,000? Well, you can just, log base 10, you just count the zeros. This is 3. Log base 9 of 3. 9 to what power is 3? Well, the square root of 9 is 3. So that's the 1/2 power. So the log base 9 of 3 is, oh, I'm sorry, I wrote 3. 1/2. Log base 5 of 25. 5 squared is 25, so this must be 2. Log base 2 of 0. So 2 to what power would give you 0? Well, I hope you realize that there isn't a real number that when you raise 2 by you get 0. So this is undefined. And log base 5 of negative 125. 5 to what power would give me negative 125? Well, this is not a real number either because 5 to any real number power will remain positive. So this is undefined as well. And it turns out that in some math classes, you can take the log of a negative number. Not in Algebra 2, though. But it would require using imaginary numbers, just like when we took the square roots of negatives. However, I'm not aware of any algebra system where you can take the log of 0. That just never works. So before we go any further, though, let's go ahead and lay down some rules that we're going to have in this class. First of all, we don't take the log of 0. We're going to make sure that the base of our logarithm is not 1 or 0. And we don't take the log of negative arguments. And we only have positive base values. So I could kind of combine rule 2 and 4. The rules for the base is that it has to be a positive number that can't be 1. A base of 1 is very uninteresting, so we're not going to use it. So we don't take the log of negative numbers, and we don't take the log of 0. So we need positive arguments, positive bases. So I want you to figure out which of these things would violate our rules in class. If it's undefined, tell me what rule it breaks. So I'll give you a minute to pause the video and try that. All right, let's discuss. Now, the log base 2 of negative 8, that's a log of a negative number. We do not log a negative number. Log base 2 of 1 over 8. Can we do that? Yeah, we can. The answer there is negative 3. So you can see that we can't have a negative in our log question, but the answer can be negative. Log of negative 2 equals 8. Well, that's not going to work either. So that's undefined because we can't have a negative number in our logarithm base. Log of base negative 2 of negative 8. Well, that's undefined as well because you can't have a negative base or a negative argument. However, this one bears thinking about because can you think of a number that if you raise negative 2 by it would give you negative 8? Yeah, you can. In fact, the answer is 3. That's one of the values. Notice I said one of the values. As soon as you allow me, though, to take log of negative numbers, I need to be thinking a little bit more. We need to be thinking a little bit more advanced, a little more nuanced. That we bring in the real number plane instead of a number line. So it turns out that we're not going to take the log of negative numbers at all, even if in this one particular case it would work. Because as soon as I move into negative numbers, things get much more complicated. So don't be tempted to think, hey, I can think of a number where that works. Because in fact, once you do that, then you have to start getting multiple answers, and we're not going to do that. So we're just going to say undefined in this class. We also do not take the log of 0. We do not use a log base 1. This one, I think you can imagine, is completely impossible. 1 to any power is 1, so you can't raise 1 to a power and get 4. That doesn't work, right? The log base 0, no, that's undefined. Log base 4 of 1, what about that? Well, that is possible. The log base 4 of 1 is 0. 4 to the 0 power is 1. Because it is very common in science, and when using scientific notation, the logarithm base 10 is called the common logarithm. The log base 10 of x is also often written simply log x. So when you see log x in this class, realize it's the same as saying log base 10 of x. So for example, the log of 1,000 is simply 3. All right, for practice, I'd like you to evaluate these logarithms, if possible, if it's not, say, undefined. So pause the video and give it a try. All right, let's see how we did. Log base 2 of 8. 2 to what power is 8? 3. The log of 100 is 2. This one here, think about what power this is. This is 1 times 10 to the negative 1, 2, 3. So if I put this in scientific notation, it would be 1 times 10 to the negative 3. And log gives you the exponent from scientific notation. The log base 1/3 of 81. 1/3 to what power gives me 81? Well, you can see that they flipped this, right? You can think this is 81 over 1. So we know the answer has to be negative so that it goes from 1 over to being a whole number on top. Then you could just think 3 to what power is 81? We actually already saw that one. It's 4. The log base 6 of 216 is 3. This is undefined because we do not take the log of negative numbers. This is a negative 2 because 3 to a negative 2 power becomes 1 over 3 squared, which is 1/9. The square root of 25 is 5, and we know that square root is a 1/2 power. The log of 100 is negative 2. Log base 4 of 16 is 2. The log of 0 is undefined, but the log of 1 is 0. The log base 3 of 1 is also 0, because anytime you take the log of 1, it's 0. The log base 9 of 27, that one's a little more challenging. We got to think of 9 to what power is 27, and it's not an easy one. But if we think of 9 as being 3 squared and 27 as being 3 cubed, then you can see that we really just need to figure out a power I can raise over here to make 2 become 3. And that answer would simply be 3/2. Because if you take the square root of 9, since the answer is 3/2, 9 to the 3/2 means you take the square root of 9 to get 3, and then cube 3 to get 27. All right, let's try this. We're going to just practice rewriting logarithmic equations as their equivalent exponential equation. So let's start with numbers, and then we'll move to letters, which will be really important for us moving forward. The log base 3 of 81 is 4. We've seen that a few times. Do you believe it? How do you know that's true? Well, we know it's true because 3 to the 4th is 81. Now let's try it with letters. The log base 2 of x is y. What does that mean? Well, same thing before. It means 2 to the y must equal x. Let's try going the other way around. 2 to the 5th is 32. Definitely true. 2 times 2 times 2 times 2 times 2 gives you 32. So that means the log base 2 of 32 must equal 5. Here we're told that 3 to the x is y. Well, then that means that the log base 3 of y is x. All right, you try. Okay, let's see how we did here. 4 to the 3rd is equal to 64. 10, remember this is log base 10 when it doesn't say it, to the 2nd is 100. 3 to the negative 2 is 1 over 9. 10 to the y is equal to x. Let's try again. This time going backwards. The log, what's the base here? 4. What's the argument? 1/16. The log base 4 of 1 over 16 is negative 2. And the log base 9 of 3 is 1/2. The log of y is x. The log base 4 of y is x minus 1. Now we're going to talk about the change of base formula and see how we can evaluate these with calculators. Use a calculator to evaluate the following. We'll need to use the change of base formula whenever we have to. The change of base formula says that if I have log of some base, I can convert it to base 10 logs by just taking the log of the argument over the log of the base. So just remember the log of the number that's more on top over the log of the number that's more on bottom. So I've got a TI-89. You could use Desmos or any calculator that you want, but I'm going to use a TI-89 today. And as you can see, they have what's called the natural log, but the regular log is on this calculator, I believe, Diamond 7. If I can get it to show up. Hold on. Well, hold on. I can go to Diamond Key. What is that? Okay. Yeah, it used to be Diamond 7. Let's see if I can find it here. Well, they may just not have it on this online version. It's not exactly the same. All right, well, never mind. I'll have to use a different calculator. That's fine. I can use a different calculator. Let's use, I do want to stick to a scientific one, though. So let's see if I can't pull up Desmos Scientific. All right, that looks pretty good. I'm just going to shrink it down a little bit here. All right, so let's start with the log of 25. 10 to, there's no even power that gives me, whole number power that gives me 25. So we'll just go here, and we're going to use log of 25. And you can see that it's an irrational number, 1.397. 1.397 would be the log of 25 rounded to 3 decimal places. Oh, actually, I should call it 1.398, shouldn't I? So that last digit made it round up. Okay, let's do the next one. The log of 351. Again, 10 to no whole number power would give that to me. So we'll just try that like this. The log of 351. 2.545. Log base 3 of 40. Well, as you can see, like most scientific calculators, this one has log, but it doesn't have log base 3. So we have to use the change of base formula. So we simply remember that the log base 10 of 40 over the log base 10 of 3 is equal to the log base 3 of 40. Remember, when you're doing a change of base, it's the log of the top number over log of the bottom. So log of 40 over log of 3. 3.358. All right, let's do one more. Log base 2 of 19. So I need to do the log of 19 and divide it by the log of 2. And we get 4.248. And I always want to discuss what this value is for a little bit while longer. We know that what we're saying then, if the log base 2 of 19 is 4.248, then that means 2 to the 4.248 power must equal 19. And it should make sense that it be something close to 4. 2 to the 4th is 16, right? And 2 to the 5th is 32. So it makes sense that it's a number closer to 2, but it's not a whole number. It has some kind of mix of a radical part and a power part. But it's even more subtle than that because it's an irrational number. And there's just a whole lot to unpack there that we're going to have to wait to fully understand. All right, I want to conclude this lesson by looking at the exit ticket today. I know we don't always discuss it, but today I want to. So let's go through these together. What is the value of log base 2 of 8? Well, hopefully you agree that it's 3. What about the log base 2 of 2 cubed? Well, 2 cubed is 8. So isn't this really the same question? So it must just be 3. And so we see this relationship that when I have the log base 2 of 2 to the 3rd power, it's almost like they just cancel out. What is the value of the log base 2 of 16? Well, the log base 2 of 16 is 4. Well, what about the value of the log base 2 of 2 to the 4th? Well, same thing. 2 to the 4th is 16. So this is just 4. All right, what about the log base 2 of 8 times 16? Well, this is the log base 2 of 2 cubed times 2 to the 4th. So this is just the log base 2 of 2 to the 7th. And as we've already discussed, this is going to cancel that out, making it just 7. Which is exactly what this is showing here, that the log base 2 of 2 to the 3rd and 2 to the 4th is just 7. You just add these exponents together. What do I think the log base 7 of 7 to the x times 7 to the y is? Well, since we added the exponents before, we can probably just add them again. And that's what I wanted you to start thinking about. All right, I'll see you in the next lesson.